Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest's Sciences and Mathematics TV channel. In our channel we deal with the different aspects of mathematics, physics and chemistry and also biology and other related topics. So today we're going to look at a concept in the spherical coordinate system, and this is the differential element. Now in our first video we had looked at the concept of the rectangular coordinate system and the respective differential elements. And we say that basically these differential elements are going to be increments which are going to be realized due to the various services, which are basically three service elements that we had mentioned, which are going to form this particular set of the coordinate system. In our case for today, we're going to look at these specific increments or the differential elements using that reference point for P that we have given using this particular variables for the spherical coordinate system for R, which is the radius, and the angle phi, which is an extension from the ZX plane, and then we're going the half angle extension from the ZX plane is going to be given in terms of phi, and then lastly we talked about the concept of a Z, which is going to form, of course, that specific Z, or rather, and also. Sorry for that, there's a slight correction. So we said that there's an angular extension which is going to form that right cone. We said that this particular service, or rather the spherical coordinate system, is made up using a cone with an half angle of theta extended at this specific point. And then therefore this is going to give us the theta element, and then we said that we're going to have phi, which is an angular extension from this ZX plane. So it's going to move along this direction, and it has a range of 2 pi radians. So therefore, we also said that we're going to have a radius, which is going to extend from the origin to that specific point on the surface of the sphere, and we give this one as point P. So therefore, apart from that, also we said that we're going to have this specific range for, so we've talked about the radius, the pi, which is a part of the cone, and then of course, angle, which is going to be the phi given as such. So we can be able to describe the various surface elements of this specific increment in terms of this specific three surfaces. So we're going to have the point P illustrated using the variables for R, theta, and phi, which of course are representing the radius, and then this is going to be the half angle for that right corner, and then this is going to be the extension of that specific plane from the ZX extension of that specific half plane from the ZX plane, of course, and this is going to be perpendicular to the X, and this is going to be the XY plane. So this is going to move in this specific direction. So the increment is going to be given as a point for P prime, and we can be able to denote the various coordinates for this specific point for R plus dr are given as an increment in the R direction given as such, and then we can be able to have this angular extension for P for theta and phi given as this is going to be phi or theta plus d theta, and then we're going to have the last one, which is phi for phi plus d phi given as such. So this is going to be a new point that we're going to have on these specific services, or rather specific service, which is going to be an interaction between these three services. And then we said we can be able to denote or give these specific services in a spherical coordinate system. Of course, in a rectangular coordinate system, I've given these ones in terms of flat services. But as we're going to see later, these ones in a spherical coordinate system, I'm not going to assume the flat surface orientation as I've given. So I've just given them for demonstration purposes. So we are going to see that the surface element for the radius ds can be illustrated using this dimension for r d theta. And of course, if we try to look at this specific part, the element for r d theta is going to be an extension from this one to this one. So this is going to be the difference between this one and this for these points, if you can be able to be seen from there. So by basically illustrated using this small arrow, this is the extension from this specific point to this one, which is going to be given as r d theta. And then we're going to have an extension for phi, which is going to be phi d phi given between this specific zx plane and this new point, which is going to be phi plus d phi given as such. So the change in this specific set for the ds, or rather the ds element, which is a differential element of this specific length in r direction, is going to be explained using the surface of rd phi, which is this one, and then we're going to have this specific surface. So basically it's going to refer this specific surface at this point, which is having rd phi and r the sine of theta d phi given as such. So this is the first set of surface element. The second one is going to be ds theta, which is going to be represented using dr, and then this extension for, so it's going to be the surface that is going to be oriented along this direction. So the first one for the drs is going to be this surface that is going to be oriented in the inner side of this specific surface. So we have got the first surface, the second one, and for the third, which is a ds phi, we're going to have ds phi as of course a surface made by dr, which is of course this specific surface, and then we're going to have rd. So this is going to be an example of this specific surface for this one, rd theta together with this one. So it's going to be a surface that is going to be, if I can be able to illustrate it, it's going to be in terms of this specific direction. So therefore we're going to have those three surface elements due to the differential increment that we have mentioned in this specific case. And this is going to represent the differential element in, of course, a spherical coordinate system, whereby we have said that we can be able to illustrate them using those specific orientations. So therefore, this is going to result in the formation of what we refer to as a differential vector, which is, of course, going to be illustrated as in our first case for the rectangular coordinate system. We are given it in terms of dl. So the vector that is going to be realized from this specific increment can be given in terms of dr for the radius, and this is going to be in terms of unity or base vector of ar, and then we said that these base vectors are going to be normal to those particular surfaces. So for the second one, we're going to have this one as a normal over a base vector a theta, and then the last one is going to be a vector which is normal, which is a phi given as such. So as I said again, these are just curvatures on a sphere surface, so therefore they're not going to be oriented as a flat surface as given. So we can be able to define this differential vector length in terms of a dr, this base vector, and then r d theta, and then we're going to have this base vector a theta given as that, and then lastly we're going to have this one as using that specific surface for d phi, r the sine of theta d phi given as such, and then we're going to have a surface element of that one given as the unity base for that one given as fi respectively. So that's how we can be able to define this vector length in a spherical coordinate system. And then lastly, I talked about the magnitude of this specific vector. So we're going to find that it's going to be given as this dl, but in terms of this specific magnitude, then therefore we're going to have to square these elements for dr, and then dr d phi, rd theta, and then we're going to also square this specific element, and this is going to be excluding those base vectors, as I said. So this is going to appear in form of and just be able to illustrate this one. So this is the magnitude is going to be given in terms of the root over dr squared, and then plus, so we're going to have the second one given as rd theta squared, and the third one is going to be given as r the sine of theta d phi and this one squared as such. So this is going to be form a magnitude of this differential length vector, which is going to be given in terms of that one. And from this we can be able to see also that there's a differential volume that we want to be formed. So from the rectangular coordinate system, we said that we are going to form what we refer to as a parallelepiped. But for this one, it's going to form a differential volume that can be illustrated as well using this dv, which is going to be given as r, is the square of r, the sine of theta, and then this element, the theta, the phi, and the r given as such respectively. So this is going to form a differential volume analogous to this that one in the rectangular coordinate system that we mentioned. So this basically is going to form a differential elements in the spherical coordinate system. And if we try to just have a summary of this, we have said that there are various surface elements that are going to be achieved from this specific differential aspect of the spherical coordinate system. And these surface elements are going to be ds, ds for that radius, the ds for this specific half angle for this the right cone that we mentioned as a second surface, and then for the third surface we're going to have this one as a plane, half plane, which is perpendicular to the x z direction, of course, which is going to be defined using phi. So the extension of phi is going to be given as d phi, the extension for theta is going to be given as d theta, and the extension for r is going to be given as dr, and the various surface elements can be defined using this specific two sets of variables, and this is for the the first one, the second, and the third. So we're going to have the base vectors which are normal to these surfaces for ar d theta and then ar theta and then a phi given as such. And from this we can be able to define the magnitude of the vector of this specific differentials using that extension. I've given this specific formula for the vector, the differential vector length, and then the differential vector volume, which I've lastly given us such. So therefore we can find the description for this various range of services that are given by just having a product of these two variables for each service aside. So for instance, for this first one, we can be able to just give it as a product of this, which is the square of r, and then we are going to have the sine of theta d d phi given as such, and then it's going to be d theta or d theta d phi given as such. So this is going to describe the surface element ds, and then the second one is the product of those two specific lengths, and then for the last one it's going to form that one. So this is going to give us a clue on how we can be able to define a differential element in a spherical coordinate system. And this is going to complement, of course, on the first two videos that we have done for the rectangular coordinate system and the cylindrical coordinate systems respectively. So catch us in our next video, so we're going to look at the other aspect of these coordinate systems, and they're going to assist us in various application areas in physics, of course, as I've said, and other areas of perhaps services and volumes in space, as I mentioned earlier. So that is it for now, guys. Bye. God bless you.